Welcome you all for the class of thermal engineering. In this class, we are going to see thermodynamic analysis of the steam flow through the steam nozzle. Already we know that what is called nozzle. Nozzle is a component which we are using to increase the speed of the steam from low level to high level before going into the turbine. And in this class, we are going to see thermodynamic analysis of a steam when it is flowing through the nozzle. Now in this slide, we are getting this diagram of a convergent divergent nozzle. This is a mostly used nozzle for all the industry purposes, and beside it is having the beside it is having the HS diagram, which is giving the representation of a convergent divergent nozzle. And in this class, I will clean up what is particularly happening in the nozzle. So we can see there are there are three sections in the particular nozzle which is there in a image. That is a section 1 is a inlet, section 2 is a throat, and section 3 is a exit. Now section 2 is a throat which is combining the converging portion and the diverging portion, and especially the nozzle is used to convert the heat amount, that means convert the enthalpy of the steam into velocity without adding any heat and without rejecting any heat, so that it is called as a adiabatic process. And also it is said to be the flow, the expansion which is taking place inside the nozzle is called as a isentropic flow. In this, I will explain. For example, if at a inlet condition, for example, when steam is entering into the nozzle, you consider the inlet conditions like you just consider the inlet conditions like H1 as a enthalpy of a steam, and P1 as pressure of the steam, and V1 as a velocity of the steam. These are the inlet conditions. These are the inlet conditions. H1 is the enthalpy of a steam at section 1, that is nothing but inlet of the nozzle, and P1 is the pressure of the steam at inlet, and V1 is the velocity of the steam. Here H1 is a very higher. Why? Because it is a very high value. It is very high. Why? Because we are making superheated. In order to avoid the wetness in the steam, for the long expansion, we are making the steam into superheated. Superheated means after getting saturated steam also we are heating it to increase its temperature. When its temperature is more than saturated, it will become very dry. So the H1 will be very high at the inlet condition, and also P1 also very high. P1 also very high. Why? Because in order to make steam for the industrial purposes, we are using the pressure of that making process about to 170 bars, 200 bars. Sometimes we are having the in the critical turbines we have, in the critical boilers we are having even 220 pressure, 220 bars pressure also. So that is P1 also very high. But when you come for the V1, that is the velocity of the steam at the inlet, this is very less, and this is negligible, and this is not low. It is negligible when you compare with the exit velocity. So these are the thermodynamical conditions of a steam when it is entering into the nozzle. At inlet, it is having H1 enthalpy very high, P1 pressure which is also very high, and V1 velocity. It is negligible when you compare with the. It is negligible when you compare with the exit velocity. Now here in the HS diagram, we can get it in the HS diagram. HS diagram we can get it. See here it clearly explaining this is the area. It is a inlet condition of the steam. See, this is the point where the pressure and the enthalpy, and this is the throat area. The second one is the throat area. Here the pressure will be P2 and the enthalpy will be H2, and here this is the third exit point. That is the third word, exit point. At this area, it is a H3 is the enthalpy and P3 is the pressure. And also we can observe here the line which is drawn vertically. It is showing from inlet to exit enthalpy of the steam is reducing. So here, what we are doing, according to the first law of thermodynamics, we know that we can't create energy and also we can't destroy the energy, but we can change one form of energy into the other form. Like absolutely, by obeying the first law here, the nozzle will convert the enthalpy or heat amount of the steam into velocity in this way. By reducing H1 into H3 level, it is increasing the velocity of the steam here, so that what is the heat lost will be what is the heat lost here. The H1 is what? H1 is a inlet and H3 is what? Outlet. According to this particular one, H3 is outlet. So it is very, it's not at all, it is also it is significantly considerable amount, but it is lower than the H1, but it is lower than the H1. So if you take it, it is lower than the H1. And the P1 is very low, P2, P3. This is the exit pressure, it is very low. Why? Because what we are doing, we are converting some amount of heat and the pressure of the steam into velocity, pressure of the steam into velocity. And here V3 is very high, it is the exit velocity of a steam in the nozzle. V3 is very high here when you compare with the V1. So that we are saying that V1 is negligible. Now here what is happening here? Heat is dropping from H1 to H3. So that the heat drop HD of this particular expansion will be H1 minus H3. Why? Because H1 is very higher, H3 is lower than the H1. So that we are writing heat drop as H1 is minus H3. So now here this is equal to gain in kinetic energy. This is equal to what? Gain in kinetic energy. KE. That is nothing but what? According to this, we know that 1 by of 1 by 2, 1 by 2, P2 square, P3 square minus 1 by 2, 1 by 2, P1 square. Here anyway, this is negligible. Which is negligible? This V1 is negligible, so that simply we can write HD heat drop is equal to of V3 square. This is the thing happening in the nozzle. And also, but this H1 to H3 is a theoretical expansion. Theoretical expansion. Expansion theoretical. This is H1 H H1 to H2 will be theoretical expansion. But when steam is flowing through the nozzle, because of the friction will be offered here when steam, for example, if these are the steam lines going through the nozzle, when they're particularly gliding over the walls of the nozzle, here friction will be offered, the friction will be offered, so that because of this friction, the steam will be added with some amount of heat. So it means that if there is any reduce in a heat drop, that is nothing but there is reduce in a velocity gain. Why? Because we are expecting from this point to this point as a heat drop, but because of the friction, some amount of heat will be added, so that when they are leaving, instead of this is the instead of this, we are getting the H4. Why? Because actually we are expecting from H1 to H3 as a heat drop. Because of the friction, we are unable to reduce some amount of heat. That means the the loss in reduction of the heat means what? Nothing but a loss in a kinetic energy. So that because of the friction, the point is going to H3 to H4. So that the practical expansion will be what? The practical expansion will be HD practical will be H1 minus H4. Here this will be greater and this will be lower. This will be greater and this will be lower. So if you want to know the coefficient of nozzle, that is nothing but K, will be heat drop practical by heat drop theoretical. So here it will be H1 minus H4 by H1 minus H3. This is nothing but known as a heat drop. This will be limited to 10%. So this is about the thermodynamical analysis of a This is about thermodynamical analysis of a nozzle. What is happening in the nozzle? In the nozzle, the nozzle is converting enthalpy and pressure of the steam into velocity. This is a function of a nozzle. And here, the expansion of the steam will be happening in the manner of a isentropic manner, and K is known as a coefficient of nozzle or efficiency of nozzle, and the efficiency will be always 90% to 95%. The 5 to 10% loss will be happens because of friction in the nozzle. Thank you for listening to this class. I am going to conclude this one. I'm going to conclude this class. Thank you.